Okay, hello everyone. Welcome to the final lecture. So maybe before we begin, a couple of quick announcements. All the previous, first of all, I'm sorry that I did not upload the last couple of lectures in YouTube. Like I was too busy for the last 10 days, but all the videos are available right now. So I have uploaded all the lecture videos, and I have also updated the self-assessment questions, including all the 15 chapters which are covered in the exam. So whatever chapters are like up to lecture 22, is it 22, 23? Up to lecture 23, which is covered in the exam. Like, so we have self-assessment question for all those lectures now, so which will be useful for your exam preparation. And other than that, we will release the A3 grading tonight. Like it's done, like it's just that I need to approve it. And also regarding the final exam, like I will send more information today, and I will also open the mock exam in Gradescope today. So just to give you some idea of like how the exam is going to be. But the exam, as I said, is going to be on December 17th, 9:30 to 12:30. Okay, so let's start. Okay. Okay, so today we will cover the frontiers in ML. So this was an introductory course in ML, like with the motivation of introducing you to the basic concepts and like the terminologies and the basic principles in machine learning, right? Like, so for the entire course, like we were focusing mainly on prediction, simple prediction problems where given some X, I was interested in predicting some Y. So this Y could be like a real value, or it could be a categorical value. Like in both cases, it becomes regression and classification. So this is what we have covered in this course. Like, so this lecture is more about what are the things that we did not cover in the course, and like what are the recent frontiers in machine learning, and like how can you learn these things, and like what are the follow-up courses that you can do to learn these things. Okay, so before we start discussing about frontiers, like, so I want to briefly talk about a couple of important things that we did not cover in this course. Okay, so what is not covered in this course? Okay, so the first thing that we did not discuss in this course is the idea of reinforcement learning. Okay, so to explain what is reinforcement learning, let's take an example. Like I would recommend you to think about how did you start learn to bike. Okay, so like what kind of supervision did you get to learn to bike? So I'm just curious, like, so can someone raise their hand and explain me how you learned to bike? Not in chat. So it's easier if someone explains it. Okay, Dana.
Well, I guess the main idea is to add some other wheels so that the equilibrium is easier to find.
Okay. Okay, but what kind of supervisions did you get? I assume you learned how to bike from your parents or like brothers, right? Like, so, or sister, elder brothers or sisters, right? Like, so how did they teach you to learn to bike?
I guess they showed me once, and then they were like kind of hovering to see if I would fall.
Okay. Yeah. So in some sense, like they were giving you feedback for sure. It is not okay. So learning to bike is definitely not unsupervised learning, right? So it's not like they gave you the bike and like there was no supervision, or like you had to figure out how to bike by yourself. So it is definitely not unsupervised learning. At the same time, this is also not the supervised learning setting that we have seen in this course. So why is that the case? Because if I have to give exact supervision on how to learn to bike, then I have to tell you like exact degree in which you should be slanting, how much pressure you should put in your legs when you are pedaling and so on, right? Like so now if you tell a kid, okay, so you have to put this much pressure in like pedaling, like it's a useless feedback because the kid doesn't know how to put exactly that much pressure, and also it is even for you it is very difficult to find these exact parameters which will help you to bike without like in a stable way, right? So it doesn't it's not supervised learning, it is not unsupervised learning, but still there is some form of feedback existing, right? Like here, like some form of feedback, and this feedback here is more in terms of correcting you, saying, okay, this is right, this is wrong, but not telling you exactly what you should do, right? Like so this is mostly about correcting your mistakes, right? And sometimes, like let's say you eventually after 2 3 days, like you learn to ride a bit without the extra two wheels, like without like debalance, like destabilizing and so on, then like your parents might also be happy, and like so they would praise you, or like they would give you some positive rewards, right? So every time like your parent says, oh okay, you're doing well, like so then you kind of figure out, okay, so this is how I should do it, and you will repeat the same actions that led to the positive rewards, right? Like so now this kind of learning is what we will call as reinforcement learning. Okay, now to give you a general idea, so reinforcement learning will have some agent which is learning to do something. Okay, so it could be learning to bike, or it could be learning to play a video game and so on. Okay, now it is going to take some action. Okay, now this action goes to the world, okay, and it results in the next state. Now this is a feedback loop, right? Like so like you pedal, and then like you move to the next position in your bike, then you pedal again, you move to the next position, like so like you're slowly moving towards your target, like in the road, right? Like so now other than just moving, like you also get some external reward from the world. Now this reward could be positive or it could be negative. Okay, now if the reward is positive, then you would try to do the same action again and again more often. If the reward is negative, like you would slowly try to reduce doing that action because you see that it is leading to a negative reward. Okay, is that clear? Okay, so now in such a setting, the goal for this agent is to learn a policy. Okay, so policy is some function from state to action that maximizes the sum of rewards over time. Okay, and the most common assumption in reinforcement learning is the rewards are usually scalars. Okay, to give you some example, let's say I want to train an agent to play a video game. Now the state is what I see in the TV, right? Like so like I see the video. Now I need to use my joystick, move left, right, or up, down, right? Like so now these are my actions. I do the action, maybe I collect some coins, so my reward is positive. Okay, maybe I touch the enemy, then I get killed, so in this case the reward is negative, right? Now the goal here is exactly to increase the number of scores that agent can get in this video game. Is that clear? Okay. Um, okay, so now that is reinforcement learning. We did not cover reinforcement learning in this course, but towards the end, like I will tell you like the like other courses to take where like reinforcement learning will be covered. Okay. Now there is also another important topic in machine learning which we did not cover, which is the idea of graphical models. Okay, so to discuss about graphical models, like we have to go back to like our naive-Bayes assumption. Okay, now maybe this is a small quiz to check how prepared you are for the exam. So can someone tell me like what is the naive-Bayes assumption? Okay, independence of what? Chat or hand raise, whatever. So what do you like independence? Like what independence of what? So what is the naive-Bayes assumption that we made? Well, IID is not in naive-Bayes. Okay, so let's go back to the Bayes rule, right? Like, so we were interested in finding P of y given x, right? So P of y given x is basically P of x given y, P of x by P of y, right? Um, Sorry. Okay, that's a silly mistake. P of x given y, P of y. Yeah. Okay. Okay, now this is Bayes rule. And now we are interested in modeling P of x given y, right? Like, so now x could be a 100-dimensional feature. Okay. Now let's say x belongs to, let's say x has 100 features. Okay. Now if x has 100 features, now this P of x given y, if it is a discrete case, then you have 2 power 100 possibilities, right? So now it is going to, like, it's a lot of parameters. So the crucial assumption that naive-Bayes did is P of x given y can be approximated with product over I is equal to 1 to, in this case, 100, P of xi given y, right? So the naive-Bayes assumption here was the features are conditionally independent given the class label. So when we learned about naive-Bayes, like I did mention that this is a very strong assumption. This assumption can be relaxed, and like there are ways to do it, right? Like so graphical models is one way of doing this. Okay, so graphical models, okay, is a general class of tools to model P of x comma y, okay, by exploiting conditional independence of conditional independence by representing random variables in the form of graphs. Okay, so we are going to consider a graph to represent all the features. Okay, now the nodes in this graph are basically the random variables. Okay, and if there is an edge that denotes conditional dependence. So it might be the case that out of 100 features, like 3 features are related to each other. Okay, in this case, like naive-Bayes doesn't capture this. On the other hand, like the graphical model would capture this dependence and like come up with a better estimate of the probability distribution. Okay, so graphical models are in some sense a marriage between probability theory and graph theory. Okay, so you will again, like towards the end, like I will give you a suggestion for a complete graphical models course as a follow-up for this course. Okay, so these are the two concepts that like I did not touch in this course. Like I wanted to introduce you to them so that you can actually go back and learn about them. Now let's get into the frontiers. Okay, so machine learning, as we have seen throughout this course, is the most promising way to achieve artificial general intelligence, or AGI as people call it, right? So there are many, if you have done a course in classical AI, like you would see that there are many ways to approach AI. Machine learning is one of them, and machine learning is definitely the most promising way to achieve AGI. Okay, now before like we get into different learning paradigms, like so I want to kind of list a bunch of capabilities, okay, that any complete AI system should have. Okay, now any complete AI system should have natural language processing skills. So this actually goes back to the very first example that we saw in the course, which is the HAL agent from the Space Odyssey, right? Like so, like a good a like an ideal AI agent should have some natural language processing capability. Like it should be able to talk and interact with humans and help them assist them in things that they want to do and be able to explain themselves to the humans as other humans normally do, right? Then it should also have some vision capabilities, right? Like you should have a strong perception module to process the visual inputs. Okay. Now, other than NLP and vision, it should also have some robotic skills, which is optional. So you would need robotic skills like only if you expect a physical realization of the system. Okay. So like if the system has to go touch, like hold, do things like humans are doing, then you need robotics. Okay, so now each of these skills are actually fields by themselves. Like so there is a lot of work which has happened in natural language processing or computer vision or robotics. Okay, so now these are all uh, like things that now you can actually go and learn, like take a course on, like after learning the basics of machine learning. Okay, now in this course, like we focused mostly on simple prediction problems, right? So these kind of simple prediction problems where I give an X to the system and it makes some prediction Y is very restrictive. Okay, so now this definitely is not the only thing that an AI system should have to achieve AGI, right? Like but on the other hand, like there are many other interesting problems in machine learning which we did not cover in this course. Okay, so this lecture is all about those problems. Okay, so let's start with let's start with the first problem, which is the idea of semi-supervised learning. Okay, now before I define semi-supervised learning, let's recap supervised learning. So in the case of supervised learning, so you have a bunch of xi and yi. Let's say I have n such examples. Okay, and given this, I want to learn a function f from x to y. Right now, this is supervised learning. So now there are some issues with the traditional supervised learning setting. So I would list some of them. Um, so sometimes labeled labeled data is costly. Okay, so labeled data is sometimes it's costly. Like for example, let's say you are working on a medical domain and every labeled example for an example cancer patient, right? Like so would require computing a bunch of features, and each features could be tests worth $1,000 or $2,000. Okay, now to get every example, it is going to be costly both in terms of money and sometimes even in terms of time. Okay, so it's time consuming. even to collect 1,000 records in a medical domain, like it might take you 5 years. Okay, so getting labeled data is hard. It's costly. It's time consuming. Sometimes it requires experts to label the data. Okay, which might not be always available. Okay, on the other hand, collecting unlabeled data is cheap. Okay, so let me give you an example. So let's think about speech analysis. Okay, in this case, my input X is the speech, the waveform speech data set. Okay, and Y is the corresponding text. When someone is speaking, I want to like have an automatic caption for the speech. Okay, now it's actually very easy to get thousands of hours of speech, right? Like all you have to do is go download these videos in YouTube and you're going to get thousands of hours of speech data. But it is actually very, very difficult to annotate them with text because you need an expert who will sit with the data set, like who will sit with the video, watch the video, like type the text and so on, right? Like it's a very time consuming process. And also like it requires a lot of manual effort, right? So now this is an example situation where it's kind of it's very easy to get X. Okay, on the other hand, it is difficult to get Y. Okay, so this is an example setting where the idea of semi-supervised learning is going to be very useful. Okay, so the whole idea of semi-supervised learning is we are going to have a bunch of labeled data as usual. Okay, so let's just call them as XL, YL. Okay, so this is a bunch of XI, YI for I is equal to 1 to N. Okay, now other than this, we are also going to have lots and lots of unlabeled data. Let's just call this as XU, which is just Xj for J is equal to 1 to M. Okay, and typically M is much, much larger than N. So you would have like, I don't know, 100 training labeled examples, but 1,000 or like 100,000 or million unlabeled examples. Okay, and as usual, you have the test data to test your system. Okay, now the idea of semi-supervised learning is given the labeled data and the unlabeled data, okay, we want to learn a function f from x to y. Okay, okay. I'm not going to give solution for semi-supervised learning. In fact, I'm not going to give solution for any of the learning techniques that we are going to discuss today. So here is a thought exercise for you. Okay, so now the kind of learning paradigms that we are going to discuss today are already well established. There are hundreds of work on this. Like, so if you go Google about semi-supervised learning, you can learn like new algorithms to do semi-supervised learning, which are often adaptations of the algorithms that we have already seen for supervised learning. Okay, now if you want to improve your ML expertise, like, so I would actually suggest you to think about each of these problems that we are learning in today's lecture and try to come up with your own algorithms before you go and Google about what is semi-supervised learning. Like I have explained you what is the problem setting, right? Like, so you have a bunch of labeled examples, you have a bunch of unlabeled examples. You want to learn the function f from x to y. So spend a couple of days for each problem. Like think about how would you solve this problem by using the supervised learning techniques that you have already learned so far. Okay, so now this is going to be a very valuable exercise, and often you will come up with algorithms which are already existing. That is completely fine. That is the point of this exercise. The point of this exercise is not to come up with your own algorithms. Okay, now let's move to the second problem setting, which is the problem of structured prediction. Okay, now so far we have seen simple prediction setups where like we wanted to predict y given x, but the y was either real values, which is regression, or it was categorical, which is classification, right? But there are so many real life problems where you want to predict something more complex than a real value or a categorical value. Okay. Now, so we are going to call those types of outputs as structured outputs. Okay. Now, to give you some example for structured outputs, sometimes you want to predict sequences. Okay. I can give you an example. Like, let's say I want to do machine translation. Okay. So given a bunch of okay, so maybe I can give you an example. So let's say I ask you, given how are you in English, okay, this is the input. I want to translate this to French. Okay, so my French is bad, but okay. Kamasawa, like I'm not sure if my spelling is correct. Okay, so now this is my output, right? Like, so in this case, input is a sequence of words and output is also a sequence of words, right? So now this is not a single output anymore. So this is a sequence, right? And similarly, like I can give you some other examples, like you might be interested in predicting trees, like for example, parsing natural language in NLP is a situation where given a sentence, I want to come up with the parse tree for the sentence. Okay. Or it could be protein structure prediction. Okay. Now in protein structure prediction, given some bunch of information, like you want to predict the structure of the protein. Now this structure is going to be a graph, right? Like you want to predict the graph instead of just predicting a single variable. Okay. Now there are like many such real life examples, like where like you are interested in predicting something more complex than y. Okay, now this is covered in the field of structured prediction. Okay, now again, that's something that I'm just introducing the problem here, not the solution. Okay, then we're going to move to the next problem, which is the problem of domain adaptation. Okay, so now what is domain adaptation? Now, to give you an example, let's say I have an image classifier. Okay, now I want to train a very good object recognition system. Okay, so if I take a picture of an object, I want it to tell me what object it is, right? You might already have such apps in your phone. Okay, now I want to train such a system. Okay, now let's say I have this huge data set of DSLR pictures and corresponding labels. Okay, say this is a chair, this is a sofa, this is a TV. So I have a lot of labels for like hundreds of thousands of DSLR pictures. Okay, now I trained the system by giving DSLR pictures as input and the object name as the output. Okay, I have trained the system, it is working well. Now I'm going to deploy this system in, let's say, an iPhone. Okay, now the camera in iPhone is definitely not the same quality as DSLR pictures, right? Like, so now in this case, you're going to see the same types of objects, but the quality of pictures is going to be different, right? Now, I want my system to adapt to this new quality of system, like quality of the images, and still give me a good performance. Okay. Now, to define this in a more mathematical way, so we are interested in modeling P of x comma y, right? Which is basically P of x, P of y given x, right? So often in some real life applications, P of x might differ from train to test. Okay, now in this case, like I want my model to adapt to this situation as well. Okay, so now I can give you another example, which is, let's take for example sentiment classifier. Given a review, like we are interested in like deciding whether this is a positive review or a negative review. Okay, so you could go to IMDb, like there are a lot of movie reviews and corresponding ratings, right? Like, so let's say I train a system using movie reviews to say whether the sentiment is positive or negative about the movie. Okay, now can I use the same system, okay, to test with car reviews? Now, this is still sentiment classification problem, right? Like, so given a review, I want to classify the sentiment. It doesn't matter whether it is movie or car, okay? But in this case, P of X is changing. So P of X in the first setup was, in the movie setup, was talking all about movies. So the kind of input that you're seeing might be more about movies, saying, oh, the movie was like slow and like, or there were a lot of unpredictable things. Like, so there are a lot of words that you will use in movie reviews which you will not use in car reviews, right? Like, so now there's a shift in P of X which needs to be handled. And how do you handle such shifts? Like, that is the problem of domain adaptation. Okay, so now before we move to the fourth problem setting, like, any questions? Okay, no questions. Maybe should I ask some of you to give me a solution for one of these problems? Okay, so let's move to the next problem setting, which is transfer learning. Okay, now let us think about how humans learn, right? So think about how you started learning to play the first video game, like probably at the age of 5 or 6, like when your parents bought you a video game. Like, initially, like, you were trying to figure out how to play the first game. Probably you could have taken half an hour, 1 hour, like, or even, I don't know, 4 hours to figure out how to play the first video game. Okay, now think about how much time it took for you to learn to play the second video game. Okay, so normally after playing the first video game, like, you would just take a couple of minutes to figure out the second video game, and you would be playing it as if you learned this video game for like several hours, right? Like, so now what is happening here? Uh, okay, so okay, yeah, I will sum up after and tell you about the sequence. That will be the last part of the lecture. Okay, so what is happening here, right? Like, so in some sense, like, when you learn to play the video game one, right? So you developed a lot of knowledge about how video games work, right? So then when I asked you to play video game 2, you were reusing the knowledge learned in game 1, right? So you were able to reuse the knowledge that you have learned in game 1, and or in other words, you transferred the knowledge from game 1, and hence you played the game 2 much faster, right? So humans don't learn from scratch. Like, when we learn new things, we always try to connect it with the previous things, and we always try to reuse the things that we have learned previously, right? So for example, let's say you pick up basketball first, then you will have some idea of like how to play, like, let's say volleyball, even though you haven't played volleyball in your life, right? Like, so like you would go start playing, and then you will immediately figure out in 5 minutes, oh, okay, this is how I should play. So like, there are many situations like where you easily transfer your previous knowledge, right? Like, so now this transferring of knowledge, for example, hasn't happened in any of the algorithms that we have seen so far in this course, right? Like, so all the algorithms that we have seen so far in this course are learning from scratch. So ML algorithms often learn from scratch. Now, can someone tell me what is the disadvantage of learning from scratch, like, every time? So what is the disadvantage of learning from scratch every time? It takes time. So more than like a precise way of putting the time is actually it requires more examples, right? So more than time, like it requires more examples, right? Like it is going to be very sample inefficient. So this is why you often see data sets having 100,000 examples of what is a cat, what is a dog. On the other hand, like, so if you show a cat to a child, like probably for a couple of times, then the third time when it sees the cat, it recognizes the cat, right? Like on the other hand, if you have to train a neural network to recognize cat versus dog, like it is going to require 100,000 examples of cats and dogs, which is something that humans don't require, right? So now this is the idea of transfer learning. Okay, so now in transfer learning, we are interested in learning one task and then transfer this knowledge to the next task. Okay, to give you an example, let's say I have an object recognition system. Okay, now we have already seen coordinates in this course. Let's say I have some image as input and I have a coordinate. Okay, now this coordinate is having a classifier on the top. Now this is a object recognition system. Let's say it can recognize 100 objects, 100 different objects. Okay, recognition system. Now I have already learned about these objects, right? Like, so now I want to transfer this knowledge to another task, which is the idea of image captioning. So given an image, I want to come up with a caption for the image. Okay. Now in this case, a simple way to transfer is to reuse the coordinate that we have already learned, right? Now this coordinate has learned a bunch of visual features. So I'm going to reuse these features and then add another system on the top of this, which will give me the caption. Okay, now this is one way to do this, but there are like many techniques to do transfer learning. Okay, now we will see one more problem before maybe we go for a break. So the fifth problem that I want to talk about is the problem of multitask learning. Okay, so in the case of multitask learning, I want to design a single algorithm or a system, okay, that will learn to perform multiple tasks. Okay, let's say I have m different tasks. So I is equal to 1 to m. Okay, now these tasks might be related, might not be related. Okay, so we don't have that knowledge. Okay, now I want a single system to learn all these tasks. Okay, I can give you an example in terms of neural networks. In terms of neural networks, like I could have the input to the neural network. Okay, now I could have multiple task heads. This is task 1, this is task 2, this is task 3. Okay, so just to give you an example, input X could be an image. Okay, the first task could be object recognition. Okay, now the second task could be captioning. Okay, third task could be image segmentation. So the problem of image segmentation is like where given an image, I want you to draw the segments of like objects in the image. Okay. Now these are three different problems. Given one image, I want to do all these three tasks. Okay. Now this is an example of a multitask learning setting. Like another multitask learning example I could give is In reinforcement learning, like I want to design one agent, okay, that can play, let's say, multiple games. Okay, now here's the thing. If these games are going to have similar dynamics, if they look very similar, then the agents can easily transfer knowledge, right? Like, however, if the games are conflicting or unrelated, then multitask learning can sometimes hurt the performance if the tasks are unrelated or conflicting. Okay. Now, can someone tell me like what is the difference between transfer learning and multitask learning? So because it looks like even in multitask learning, there is a transfer happening between different tasks, right? Like you're sharing the knowledge between the tasks. So now what is the difference between transfer learning and multitask learning?
And also, Sarath, can you elaborate the differences between domain adaptation and this learning, transfer learning also?
Okay. Okay. So we will come to that. So now can people okay, first maybe can we answer what is the difference between transfer learning and multitask learning? So there's a question. So how can you define the related task? That's a good question. In general, we don't know if the tasks are related or not. So it is also part of the algorithm's job to decide which task is related to which and like make use of that connection. Okay, so in multitask learning, we want to do everything at the same time. Okay, so in some sense, multitask learning is parallel because you want to learn all the tasks at the same time. And transfer learning is sequential because you learn the first task and then you move to the next task. Any other differences? Any other differences that you can think of? Okay. Okay, what kind of transfer is happening in transfer learning versus multitask learning, right? Like, so in the case of transfer learning, okay, it's actually a one-way transfer. You always transfer from task one to task two, okay? But in the case of multitask learning, it's in some sense all-way transfer. If you have two tasks, you will transfer both from T1 to T2 as well as T2 to T1. Okay, is that clear? Okay, so there's a question. I think we retrain in between tasks for transfer learning. In the case of transfer learning, like you typically train on the first task, then you train on the second task and you expect to do well. Okay, is this clear? Okay, so just to recap what we have seen so far before we go for break. So we looked at the problem of semi-supervised learning, where right, like so where the idea is getting a lot of labeled data is costly. So can we also exploit the unlabeled data that we have to improve the performance? Then we looked at the problem of structured prediction, where the idea is like instead of just predicting a simple X, can I also predict simple Y? Can I also predict some complex structured wise like graphs or trees or sequences, right? Then we looked at domain adaptation, which is like it's the same classification problem, but the distribution of X might change, right? And then we looked at transfer learning. Okay, now I think this answers the question like the Charan raised, like which is what is the difference between domain adaptation and transfer learning? Typically in transfer learning, you move from one task to another, but in domain adaptation, like it's the same task, it is just that the X distribution of X changes. Okay, so then we looked at multitask learning, which is the idea of learning multiple tasks together. Okay, so towards the end of this lecture, like we will also have a discussion on like how all these paradigms are related, because in some sense there is no clear boundary between these paradigms. Like so, like there is a bit of transfer learning involved in multitask learning, and and there is a bit of domain adaptation involved in transfer learning and so on. So these are not like disjoint set of learning paradigms. Okay, so I think we will take a short break here. Okay, maybe I'll answer the question. Is there any questions before we go for break? Is there any relation between bidirectional networks and multitask learning? Well, no. So multitask learning just means you're learning multiple tasks, right? Like, so bidirectional networks are different. Is there any other questions about the problems that we have learned today before we go for break? Okay, so I will talk about unsupervised learning. Okay, so maybe I'll just finish it off. So, well, in some sense, we have seen. Okay, I kind of agree that most of this course was focused on supervised learning, right? Like, on the other hand, we also looked at a few unsupervised learning problems. It is just that we didn't we did not have time to cover more unsupervised learning. So, in the case of unsupervised learning, the whole idea is like you are just given a bunch of X. Say for I is equal to 1, 2. I is equal to 110. Like you're just given a bunch of xi and you are expected to do some task. Like it could be as simple as dimensionality reduction, which we have already seen. Right? Like in the case of dimensionality reduction, there was no y. Given a bunch of x, I want to reduce the number of dimensions. Right? Like, so there is also clustering, which I wanted to cover in the course, but we did not because of the lack of time. In the case of clustering, given a bunch of data points, like I'm interested in grouping them based on the similarity, right? And so to give you an example, let's say I give you a bunch of news articles. I want you to group them based on the topic. This is clustering, but the catch here is like I don't know the topics beforehand. If I know the topics beforehand, then it is a classification problem. Okay. Okay. So how to approach semi-supervised learning problems? Well, as I gave as a disclaimer in the beginning, I am not giving solutions for any of these learning paradigms. So I would let you think about how to solve semi-supervised learning. And after a lot of thinking, I want you to go back and like look for resources to look at algorithms that solve semi-supervised, like that solve semi-supervised learning problems. Okay, so can we evaluate an unsupervised learning algorithm with supervised? Well, yeah. So for example, like even in clustering, sometimes like you have data sets with labels, but you will not use the labels. Like you will run your clustering algorithm. And then when you evaluate, you could use supervised metrics for evaluation. That is fine. Okay, any other questions?
And Sarath, the methods you have said, domain adaptation, transfer learning, they can be unsupervised also, right?
Yeah. Oh, they can be unsupervised too. Like, yeah. Oh, it's just a problem, right? Like, so you can solve that in supervised way or unsupervised way or even semi-supervised way. Okay, so there's another question. You want to use unsupervised learning for denoising. Can I use it?
Yeah, autoencode, right?
Yeah. So, well, there are ways to do that. Yes. Maybe check for denoising autoencoders, but like in a much more general way, you could actually learn to corrupt. Like you could have like a manual corruptions in the examples by yourself, and like learn to correct these corruptions, so that when given a real corrupted data set, you can try to recover the original X. Okay, so I think we will stop now for a break. So I'll stop the recording and